Let us consider some examples of Lebesgue spaces. So let us recall the notation for the Lebesgue measure. So the Lebesgue measure in Rn will be denoted by lambda n, and the corresponding outer measure will be denoted by with a star. So this is the Lebesgue outer measure on Rn. Okay, so with this, recall, or we denote by a sigma n star the sigma algebra of measurable functions. Let's say Lebesgue measurable functions, or measurable sets, I should say. And recall that by measurability, we mean in the Karate-Dori sense. That is, so A is Lebesgue measurable if and only if for any subset E and Rn, the outer measure of E is equal to the outer measure of elements in E that is also in A, plus the outer measure of the set in E that are not in A. So these are Lebesgue measurable sets. So suppose I have a measurable set, Lebesgue measurable set omega, let us consider the restriction measure. To be precise, restriction Lebesgue measure on omega to be the following. So lambda n omega. So it is defined on measurable Lebesgue measurable sets in Rn. To 0, to infinity. So how do we take the Lebesgue measure or the restriction Lebesgue measure of this measurable set A? We simply take the Lebesgue measure of the intersection of A and omega, because the measurable sets or Lebesgue measurable sets form a sigma algebra. Then it's clear that here you have an element of this collection. Okay, so by the way here, lambda n is defined on the measurable sets, while the outer measure is defined on all subsets of Rn. Okay, so that's the difference between these two measures. Well, the other one is only an outer measure. Okay, so in this case, instead of having this notation for this Lebesgue space, L omega measurable sets restriction measure with values in y, we simply denote this by LP omega y, having in mind that the measure is the restriction measure on omega, and the sigma algebra is the sigma algebra of Lebesgue measurable sets. Also, we will denote by LP omega to be those functions that take values in the field K, either of the real numbers or the complex numbers. So this is to simplify the notation for the Lebesgue spaces. This is our typical Lebesgue space that we consider in real analysis. Next example. In the discussion on Banach spaces, we mentioned that the little LP spaces are Banach spaces. Okay, but we did not give a proof there. So in this case, we will provide a proof. So we will view the LP spaces, the little LP spaces, as Lebesgue spaces. And here we consider, let's say when P is finite. In fact, it will be also valid for P equals infinity. Okay. So let us recall this little LP is the set of all functions x or sequences such that x sub k k from 1 to infinity raised to p is finite. And recall that this is the little LP norm raised to p. So we would like to write this little LP space as a Lebesgue space. So to do that, let us assign. Okay, so this is your x and this is your y. We need to put a measure on n. So for that, let us consider the counting measure space. What is the counting measure? So the counting measure is defined on all subsets of n. So from the name itself, the counting measure of a subset A of n is the cardinality of your set if A is finite and it is infinity otherwise. One can check that this is indeed a measure on n. Okay, so let's start with, let's say, a function x from n to k be in LP. Okay, so this is your set, this is your sigma algebra, this is your measure, the counting measure, and the value is in k. Here we will only consider the case where p is finite. When p is infinity, one can adapt the argument in a similar way. Okay, so here, let us truncate this. Okay. Let us define x sub k. What is k? So for each positive integer k, let us consider the truncation x sub k. So this is a sequence wherein we have, let's say, x sub k is equal to x times the characteristic function of the integers from 1 to k. Or you can write this as simply as the sum j from 1 to k of the indicator function, or let's say the value of the function at j times the indicator function of the singleton j. So take note that this is a simple function, since here this is obviously a subset of n, and these are measurable, because here all subsets of n are measurable with respect to the counting measure. Then you could easily see that you have this convergence as k goes to infinity, pointwise, and you have this bound. In n for every k in n. So you have pointwise convergence, and this one is integrable, or I should say the power is integrable. Applying the Lebesgue dominated convergence theorem, okay, starting let's say from the LP norm of this sequence x raised to the power p. So by definition, this is the Lebesgue integral over n for the absolute value of x raised to p with respect to the counting measure. Okay, and as I said, by the Lebesgue dominated convergence theorem, then this is equal to the limit of the truncations. Okay, so here if you put inside the limit, you have the power x raised to power p. Okay, let's put p here as a correction. Now, since we have a simple function, and take note that this is already in canonical representation or in canonical form, then this integral of the simple function is the sum j from 1 to k of the magnitude of x sub j raised to p, okay, times the measure or counting measure of the singleton j. This is a singleton, hence the counting measure is 1. And this is, in fact, the series xj raised to p. So let us now change this to infinity. And this is nothing but the little LP norm of the sequence x raised to the power p. Okay, and you can work the converse as well. Therefore, the little LP space is identical to the Lebesgue space LP with domain n with respect to the counting measure and values in K. Okay. So one can also establish this in the case of when p is equal to infinity. Take note that essential boundedness is equivalent to boundedness since the only set having measure 0, or the only null set in this case is the empty set. So essential boundedness is the same as boundedness, and you get the same in the case when p is equal to infinity. Okay, since this is complete, therefore the little LP spaces are also complete. And that's the proof of completeness of the little LP spaces by appealing to or writing it as a Lebesgue space with respect to the counting measure. And for the final example here, let's talk about, let's say, iterated Lebesgue spaces. This will be clear at the moment. So consider two measure spaces, x sigma mu and y tau nu. And let us suppose that they are sigma finite. Then, okay, let's start with the Lebesgue space on x. And then one can take the Banach space y, say LP, yt nu. So this is our Lebesgue space y. Think of this as the Banach space y in the previous discussion. So now it's clear why we call it iterated Lebesgue spaces, because we have a Lebesgue space wherein the values are also in a Lebesgue space. Okay, one can apply the Fubini theorem to say that this is isometrically isomorphic to the LP space with respect to the product. Here you have the product of the domain, you have the product of the sigma algebra, and the product of the measures. And in fact, you can interchange the two, again by the Fubini theorem. Of course, when p is finite. However, when p is infinity, these two are not necessarily the same. So in fact, one can only at least say that one is a subset of the other. So this iterated Lebesgue space is a subspace of this product Lebesgue space, or Lebesgue space on the product. And there are examples wherein we don't have equality in general. There are cases wherein these two are equal, but if let's say x is the Euclidean space, then this is not valid. Okay, so these are some examples of Lebesgue spaces that we will see in future discussions. In the next lecture, we will discuss the concept of differentiability, or more precisely, weak differentiability for Lebesgue functions. See you there.